Okay. Yeah, so let's continue. What's going on here? This is an old thing. So, yeah, okay, good. So what's next? So let me just deduce another corollary out of these. Okay, so that's why this was premature, because currently I don't know the dimension of a Riemann-Roch space of a divisor is finite, but we do in the next slide. So that's why this appears later. So for every divisor, the dimension is finite. And recall, this is a notation. I should have said that. It's the dimension of the Riemann-Roch space of A, as a vector space over K. Just a notation. And that kind of makes sense. I don't know. So divisor, you only allow and require finitely many things. You don't expect infinitely many functions satisfied. Right? I mean, you actually require infinitely many things because the zeros are requirements. You're only allowing finitely many things. Sorry? Yeah. Just a reminder. It appeared here, I think. Well, it was defined for B. Okay. Right. So the proof is like a very kind of underwhelming, but it's obvious from that. So you just need kind of to use the theorem. Not that, the theorem that was here, in which I erased. That is a corollary of that, actually. So, okay. So you take any negative divisor, you want, -1, all zeros, I don't care. So by the previous lemma, which we just erased, we know that, sorry, the dimension as a K vector space of the quotient, you see I still have quotients, I can't still separate them, because I don't know anything is finite, is at most the difference of degrees. And what do you know about this thing, like this little, maybe I should be more original in following schemes. What do you know about this thing? So, this is a negative divisor, right? It's even smaller than B, potentially. It's 0, exactly. So it's like, as a Riemann-Roch space contains nothing, that's what we said. If you have a negative divisor, in the sense that we talked about, then the Riemann-Roch space is 0. If you only require 0. So this means, okay, so you actually quotient by nothing. You see, I could have taken any negative divisor, but I also needed to be smaller than A to apply the lemma. So I just combined them. I took a negative divisor and something that's smaller than A and did it like that. So this is the dimension of LA, right? And that's finite. I mean, just divisors. These are divisors, everything is finite here. Right, and also take B to be a divisor, just to make sure. Yeah. Right, so it's underwhelming, but you see, and now once you have this, you can say what I said here. You can separate the dimensions. Now we know that for divisors, dimension is finite, so you can do this, and we'll call this the monotonicity of the deficiency. No one calls it like that, but we'll call it like that, the monotonicity of the deficiency, because the deficiency respects the order of the divisors. The intuition is, by the way, I said it in the break, but the intuition is that why is there a deficiency at all? There is a deficiency because initially you allow one more pole, remove a restriction of a 0, whatever. When you move from A to B, you allow one more pole, and you may not get a function in return, a new function. You still have all the previous functions, but you may not gain a new one. And why won't you get a new one? Because of the algebraic relations between the functions. So maybe this new allowance, that you allow one more pole, is already kind of given by the algebraic relations. That pole is anyhow given because of the relations of the functions that are already there. And as you increase A from B, as you go up and up, you accumulate more and more algebraic relations. So you lose more and more, like the efficiency increases. Initially, at the beginning, you're small and you don't see the entire algebraic relations of the curve. But as you go higher and higher in the divisors, you accumulate all of them. And actually, with this set in mind, you might expect this is a finite number even, because how much things you can accumulate. And that's Riemann's theorem. Really. That's what it says. So it's a finite number, and that finite number is essentially the genus of the function. But let's do it slowly. So we essentially proved Riemann's theorem. You'll see the proof. It doesn't look like that at all. Okay, so we did all that. Right, and one thing that I will use, but I'm leaving you as an exercise, I think it's probably in the problem set, I'm not sure, is that we can actually say more. Not only, it's actually kind of obvious, but I won't say, it's actually a very easy exercise. So it is really an exercise, like in the sense that you take 1 minute to think about it. So what I'm saying is that for every divisor, but non-negative, like in this sense, every entry is non-negative. The dimension of A is at most, not only it's finite, you can bound it by the degree plus 1. Like, for the plus 1 is just because we counted improperly. So like in polynomials, right? So if you take, the Riemann-Roch space, this Riemann-Roch space, so if you take A to B, e.g., A to B R times P infinity, all polynomials of degree at most R including R, then the dimension is R plus 1, right? Because you have 1x up to x to the R. So that's why the plus 1. The plus 1 is just because they weren't computer scientists. They counted from 1 and not from 0 in a sense. And they fix it in the definition of the genus, you'll see. But that's an easy exercise that you can do. It follows immediately by lemma 14 also. Now we are just using the fact that it's also a non-negative divisor, that's it. And there are some other exercises in the notes that you can look at, but let's not consider them. Any questions? Good. So now we are moving to unit 11, which is called Riemann's theorem. And it's not so fair to call it Riemann's theorem, by the way, because he didn't prove it. And the genus, I think the one or the people who proved this were, like for function fields, were like maybe, I think technically it was initially Dedekind and Weber, and then people like Artin and Schmidt kind of extended that theory when other people like Düring and Weil and Hasse joined. So it's not, Riemann didn't know about it. He died before any of it happened. But he proved it for the complex Riemann surfaces. And the proofs weren't like quite proofs. People actually worked hard to make it formal. Okay. Yes. The intuition of that, it actually does make sense. Like if like the zero divisor, maybe I should say, the zero divisor has degree 0, and you get all of k in the Riemann-Roch space. Right? L of 0 is k, if you remember. So that's the one. Right, so that's a good question. L of 0 is k. We didn't prove that. We said it's obvious from the thing that appeared here. It was an exercise. But even a degree 0 divisor, like the 0 divisor, which has degree 0, gives you k, which is one-dimensional over k. And then every like additional freedom that you give me shouldn't give you like 2 functions, only 1 function at most. Like, so you can't have like, right. So that's why it happens. This starts from 0 and this starts from 1, because here, because you're strictly, I mean, A is a larger than 0. So I'm starting from 0s and I'm adding primes up. So initially it's 1. When this is 0, this is 1. And then you expect, I mean, it's also not hard to prove, given what we did, that if you allow 1 more prime, you don't get 2 more functions. So it's always, it's a kind of by induction you can do it. Yeah, that actually implies, yeah. Right. Actually implies that immediately. Right. But the intuition is like just before formal stuff, you allow one, you don't get two. You get at most one. That's what's written here. Right, because of the degree of the prime divisor, you say. Right. Right, the irreducibility degree 2 or something. Right, right, that's good. And when the degree goes up by 2, then this may go up by 2. Also, yeah, that's a good point. Yeah. Okay, so let's start this unit. We are going to actually prove, before even proving Riemann's theorem, we're going to prove a very serious theorem, which I think is essentially Bezout's theorem. Yeah, quite sure. I think so. It implies, I think, Bezout's theorem. And Bezout is not easy to prove. It's actually not easy to state. And we're not going to do that, but we did more. Like the machinery that we have, like easily kind of express Bezout's theorem, and that's what we'll have today. But before that, just a definition. So say you have a function field, and you take an element x, and let's say it's a non-zero element. Right, so if you remember, we had this principal divisor, which we called principal divisor, but we never proved it as divisor. Potentially, it could be a pseudo-divisor. Right, so the name is like suggesting that we know something that we didn't prove, and that's the case, and we'll prove it now. But this is the principal divisor, that's how it's called. And right, and as you saw in the Riemann workspace stuff, the negatives and positives are really different. So you want to kind of consider them apart. Right, the positive tells you you are allowed to have poles, and the negative tells you, in the Riemann workspace of the divisor, you are required to have zeros. And the zero tells you are not allowed to have poles, but you are not required to have anything. So what we are going to do is we are going to define the two divisors. We are actually going to define two pseudo divisors, but we are going to show they are divisors. So this is going to be called the zero divisor. So it's the same notation as principal divisor, but with a little zero here. And what I'm doing, and from out of this sum, I'm only taking those with positive valuation, like the zeros of the function, not the poles. So it's part of the sum, in a sense, right? So again, that's a pseudo divisor as far as we know. Right, all the poles, I just list all the poles of x, all the zeros of x. And similarly, I'm going to denote by this kind of principal divisor notation, sub infinity, the pole divisor. So I'm only taking the minuses, but it's actually nice to flip them so that we have a positive divisor. So it's minus. It's, you're taking the poles, but you don't, you make them feel good. Also a pseudo divisor. Good. And now we are doing the biggest step. It's going to be a bit difficult to prove that these are indeed divisors. Okay, so the following is, okay, sorry, names. This is the zero divisor of x, and this is the pole divisor. This we'll see them on and on. We care about this. It's not just a technicality in order to prove something. Okay, so I don't know, maybe for example, if you take a x in the rational function field, what is x in the rational function field? Like, what's the principal divisor of x? Exactly. Right, it has 1, 0 at 0 and 1 pole at infinity. And so, kind of nicely enough, this is the zero divisor, and the pole divisor is that without the minus. Like, so x is always like x0 minus x infinity. Okay? Just breaking it down, that's it. Oh, keep losing pages. 16? Oh my God, what is 16? 12, 17. 18, 17. And like, okay. This is, no, wait, this is now. Oh, I'm not even, no, what am I doing? So I got confused for a second. This is way, this goes like that, that, that. Yeah, good, sorry. So I almost derived corollaries from Riemann's theorem. So this lemma, it seems like, oh, now I know it. I kind of partitioned it so it won't be heavy. And then I took the other one. Okay. So this is a big lemma. Okay. A big step. So you have a function field. You take a non-zero element x, because zero is not interesting, because also we don't have the zero divisor technically. It's like infinitely many zeros. So like it has zeros everywhere, infinitely many infinities. So I don't write it. And what I'm claiming is that take any s like that which is finite, take any set of primes which is finite, you're only allowed to take finite number of primes that kind of participate in the zero divisor. Right, so you take your x and you pick some finite set of its zeros. Like this is s. And finitely many p's, you collect them as s from the zero divisor. And what I'm claiming is that if you look, I think that's the last time that we will see it. If you look at the truncated version of the principal divisor, it's at most this number. Right, so again, you take an element, a non-zero element, potentially it may have infinitely many zeros. We want to prove that's not the case. And also poles, but let's start with zero. It's the same thing. So you take any finite, still finite subset of its zeros. I mean, I know it has a finite number because I know it, but we don't know it yet. So you take any finite number of its zeros, that's S. And what I'm claiming is if you are going to restrict the principal divisor to S, so that's even a bigger, I mean, that's also a restriction of x0, like the zero divisor, because I'm only taking zeros of x. But if you are looking at the principal divisor restricted to S, you get a bound. And what is so special about this bound? Exactly. It doesn't depend on S. It's finite, some finite number. It's finite. Oh, it's actually two things. It's a finite number that doesn't depend on S. And that would kind of immediately imply later that you can only have finitely many zeros. I mean, it implies right now. You can only have infinitely many zeros. Because if you have infinitely many, you can kind of add them to S one by one, increase this number all the time. It's always increasing by at least one. But that's a number that's independent of S and it's finite. Because we said that this is a finite extension in function fields. So that immediately implies, I'll state that later, that indeed every function has finitely many zeros. Any guess as to how many zeros that function has? I mean, the only guess that you can give in the question. How many zeros does the function have? This number. So that's an inequality, but it's going to be an equality later, like right after that. But the first step is to prove this. From that, it is immediate that function have finitely many zeros, and also finitely many poles, because you can look at x inverse. Yeah, fundamental. Exactly, it's essentially fundamental theorem of algebra. And that's the easy direction. Like you can't have too many zeros. And the hard direction is the equality, which you have those zeros. exactly. And poles is the same because you can put an inverse here. It doesn't change k of x because k of x and k of x is the same field. And when you put an inverse here, the zeros flip to the poles and the poles flip to the zeros because the evaluations get minuses. Or, it's like 1 over. So that's why this is a key lemma to prove. Kind of kills everything later. Right, because it's a function field, and x is in. Oh, you're right. Yeah, no, but technically right. If x is in k and not in f, but that's infinite. But if k is in k, then we know it's principal divisor. It has no zeros anywhere unless it's a zero function. So only when x is in f and not in k, this is a finite number, but that's the only interesting case anyhow. The proof has that in there, but good. I was thinking of x, which is a proper function, not a constant. Because constant have no zeros, unless it's zero and we don't care that. We understand those, we don't need Riemann to help us with understanding zeros, the constants. So, good. So let's see the proof. Yeah, it's going to be like interesting. Okay, and actually the proof starts with the assertion is trivial for element in K, because this is just infinite. If X is in K, this is transcendental extension, it's infinite. So let's assume. Yeah. Because S is only taken, these are only primes, which are zeros of F. S is not taken any set. It's a finite set, which is a subset of those primes that PP of X is also. Of X, yeah. And it's a finite set of zeros of X, exactly.
No matter what finite set you're taking this.
It's only 16. This number is only whatever, the right hand side. So you can't add more and more zeros because 16 will stay 16 and the left hand side will increase and increase as S increases, at least by 1. If you take a prime divisor with degree larger, it increases by 4 maybe. Good. So assume, right, let's start with this. Assume the x is in F, not in K. Because K is easy. And just for us not to carry it around, let's just denote A by this divisor by A, just being lazy. And as a reminder, that's exactly this thing, and it's a positive or at least non-negative divisor. Because these are always positive, like strictly positive. It can only be 0 when it's empty, I think. I'm just denoting it by name and writing it as is. Now we did prove in the truncated version equality of the quotient to the difference of degrees. That's how we started today and ended last time. And the difference of degrees is what exactly in terms of A itself? So deg AS is like supported on S anyhow. So deg AS minus deg of the zero divisors supported on S is what? The degree of A. Right. Because everything is in S, like in A. A is X restricted to S. So when you restrict it, like again, nothing happens. So that's the degree of A. And that's the general philosophy I told you. Whenever you have, like this is the degree of XS. So whenever you have a number which like has no meaning, like it's a sum of whatever numbers times whatever, and this is a number that you understand. You see it's the extension from that. You really need to give this a meaning. So now you gave this meaning. We knew that it's really this dimension of this quotient. So now I understand this number, and we're in a better position to understand why this is smaller or equal than that. When we want to compare this quotient with the quotient f over k of x. Right, you see, now it makes sense. So it's all about finding the right structure that give you the number. Okay. So what we'll prove, so this little philosophy implies that it suffices to prove that for any k, any number k that's larger than what's written on the right-hand side, it's a finite number. So for any k that's larger than that, any y1 up to 1k, any k elements here are linearly independent, like when you walk here, we walk modulo that, are linearly independent, linearly dependent, so yes, exactly, over k modulo, like they're linearly dependent here, but I'm just writing that over k modulo L0s. Right, I mean, you want to prove that this has lower dimension than that. So you take any k elements, any too many elements for the right-hand side, any k elements for a number k that's larger than that, and if you prove that they are linear, these k vectors are linearly dependent as elements here, or put differently, they are linearly independent over k when you modulo out by L0s. That's a computer science thinking, you think. Either working in F5, you work in Z, and then do mod 5. Same thing. Then you're done, because it means that the dimension of this can be larger than the dimension. Just think about this logic for a second. Is it okay? You need to kind of.
So that this vector spaces have this number as bound to the dimension.
Right. So you have this number. You take any number that's larger than that. Usually you do the other way around. But here you take a number that's larger than that. Namely, okay. So, but this number has a meaning. So larger than this number, which has a meaning. And you take any k elements here. Then you want to show that these are dependent modulo k over k modulo this. Right. Exactly. Oh, yeah. Good. Even more explicitly, what we want, given these y1, let me just interpret that, write that again. We want, given these y1 up to yk, again, I fixed k already. We want to find a1 up to ak, little k in capital K, not all zeros, don't cheat, such that right? That's what's written here in math. Like, you want that for any y1 to yk, you want them to be linearly dependent over k modulo this. So over k means modulo this means that for this set of y's, you can find like scalars, a1 up to a little k, not all zero because that's not fair. That doesn't imply the linearly dependent, such that this linear combination of the yi's that you got according to the a's that you found is 0 modulo L0s. So it's in L0s. Okay, is this clear? That's what we want to do at this point. Questions? It's a bit confusing. It's okay. So the question is, where can you find these AIs? I mean, you don't have, all you know is that y1 up to yk must be linearly dependent over kx. Right? Because they are coming from f. I mean, they're coming from here. But this f is everything. Like the field f contains all functions. So these functions that are coming from here are actually coming from f. So these functions are in f, and you know that they are linearly dependent over kx. So you do know that you can find polynomials that, like in x, that rational functions that linear combinations to make this vanish, but you don't know how to find like constants, right? But you do know how to find the polynomials. You know there are polynomials. Like for rational functions. Let's call them. So what do we know? We know that we know that as k is larger than fkx, we know that there exist rational functions, like element here in kx, not all zeros, as element of these fields, such that it looks the same, but that we know how to do, because k is too large. Any k elements here are going to be linearly dependent over that. But we want numbers, like in a k, not rational functions of k. So essentially, what would you do? Substitute. What value would you kind of substitute? Hopefully, don't worry too much. There's only one number. 0, yeah, we're going to substitute 0. Of course, one of them may be 1 over x or something. So we are going to clean denominators. But essentially, we are going to get the constants from these functions by substituting 0 after making sure that we can substitute 0. Right, so it's like right. Right. It's not going to be exactly. It's not going to be 0, 0. Yeah. Here it's 0, 0. You just want it to be in LAS. L0s. Yeah. Thanks. So yeah. So first of all, we can immediately assume that all FIs, without any worry, they are polynomials, right? Why? Right. Multiply by the product or LCM or whatever of the denominators, and it's polynomials now. It's still not 0. I mean, not all of them are 0, and this is still 0. And you can also assume that not all of them are divisible by x after you did this. Not all FIs are divisible by x after you did this. Why? Right, because you can just you can also, after maybe initially you can do it cleverly, and if you multiply by all of them and you got everyone divided by x, you can just divide by x and remove the minimum amount of x's. I want that because I want to plug 0, and if all of them are divisible by x, then plugging 0 will give you 0. I don't want that. Good. So now let's write fi of x. I want to isolate the constant, so it's like this plus constant. This is really fi of 0, but I'm writing it like that. Well, now j of x is a polynomial times x. Okay, weird way of writing it, but and this is the AIs that I'm going to prove. But why 0 is in L0s? It's always there. It's always there. That's a good point. I mean, it's not so trivial. So we're missing something, you and I, right now? Ah, yeah, good. That's the point. Thanks. No, the coefficient could be, sorry, no, that's not it. Yeah, it could be in K. The question was, Yuval says, we are done because you can't plug 0. Okay, Yuval is saying, just plug 0. Like this is the rational function. You can plug 0. It's not like weird, I don't know. So fi of 0 is j of 0 plus ai. So when you plug 0 here, you get only ai times yi. But when you plug 0 to x, you also change yi because there are algebraic relations between things. So maybe yi is 1 over x, or what, It's not like independent of the x's.
It's not a variable.
X is not a constant.
It's x from the start, right?
Yeah, but the yi's that you found may depend on x. Right. That's a great question. Right. I mean, you would say, just plug 0, right? If you plug 0 here, you get AI times yi. It's yi when x is 0. And I don't know. I want to talk about these yi's. Good, very good. Yeah.
So you get that, like, so you get something.
Right, you can, because x, right, x is a function. And the y, I mean, you were given, and you started with an x. I don't remember. No, you can look at, you're right, but I mean, you can look at phi of when it's phi of 0, like substituting, I mean, I'm applying the phi function at 0. So yeah, technically I should do a phi here, but the point is that if you substitute x0 for x, you kind of essentially degenerate the yi's to be some finite from a finite set. Like maybe this is y squared. Right, exactly. And there are algebraic relations between them. I can't change that without changing. Like if I do phi on this, okay, it will go through the fi's, but it phi of x, and it will have here phi of yi. It's not yi anymore, right? Yeah, that's a good point. Okay, but so let's continue on with how it should be. So right, so we want, so it is enough. So we wrote this fix as a polynomial multiplied by x plus the kind of leading coefficient. That's still fair to say. And so it is enough to prove that. So I'm writing something which is true. Oh, so I'm writing this. So it's enough to prove. No, so this is true. Let me write. Right. Once you have this notation, you can split the fi according to the A and the GIs. And so now it is enough to show that this thing, with the minus or without, it doesn't matter, is in L0S. I mean, we want this to be in L0S. We want to find AI is not all 0 in K, such that this is in L0S, but that's the same as this, so it's enough to prove that. And the minus doesn't matter because it's a vector space.
It doesn't have poles on this, right? That's what.
Exactly. Right. And now, right, so far we use black box. We didn't even look at this definition. We just laid out, and now you have to open it up in order to prove this. And actually we will prove this. I mean, there is no hope to proving it to that sum. You're just going to prove it to any summand because you don't understand the sum. So we're actually going to prove technically something stronger, but no way you can prove otherwise. So we are going to prove this. Right, so it's it's x times this, and that's all you know. This thing?
Yes.
X times k of x. Right, no leading coefficient. No constant coefficient. It's x times another polynomial. Okay. And as Yuval said, now we have to really remember what is L0 of S and all of those because we didn't use it. It was just like there. So right, so let me just do, so what we want to prove? We want to prove that for any, so what we're going to show is that for any polynomial like that, and y, any summand, any yi, so I'm just removing the i's really, and we know that the y's are coming from LAS, that we know, we want to show that gxy is in L0S. And that will conclude the proof. Okay. Okay, so let's see. So, you have this S thingy. So let's do prime divisor by prime divisor. So let's fix P in S. And we know that VP of X is larger than 0. And I forgot why really at this point, but Why? I don't remember what is x at this point. So I ask like I know. Why is this true?
S is the all P and S. That's the start, the definition of start. All P and S. S is of the zeros.
Ah, yeah, right. Yeah, good. P was in right. Was S P is an element in S, and S was only the zeros of X. Thanks. Yeah, good. So yeah, some lecturers are good enough to just write it like and omit, their kind of hide, but I can't do it. So okay. So by the definition essentially of S, this is slightly larger than 0, and this I claim implies. I mean, not this, and we also know that I know that VP of G of X is any polynomial in X. Like multiplied by X, or X times the is at least this. Actually, we did it at some point, like in the informal part. We said that if you have a polynomial, maybe ax squared plus bx and stuff like that. Here it's really like that. You don't have a leading coefficient. So we said, right, so the valuation, I'm just reminding you, right, this is true. The valuation of this, technically it's at least the valuation, the minimum of the valuations. If you remember, that's a non-strict triangle inequality. Now, the coefficients don't matter because a coefficient which is non-zero, I'm not writing the zero coefficient. The coefficient which is non-zero is 0, VP of that is 0, because a valuation of a function field is trivial on F and non-trivial on K. And when we did the example, we didn't have a function field and just proved it with z to the q minus z. Right, exactly. So I used a trick to do it, which I'm proud of, but never mind. So I shouldn't be proud of being proud of it. So the valuation of this is that, and that's 0 because you're in a function field and A is in K, so the valuations are trivial on A. I mean, if this is 0, that's infinity, but that's not 0 because if this is 0, you don't write it. So it's like that. And now, because VP of X is larger, strictly larger than 0, then this is strictly larger than 0, and this is by the same reasoning VP of X. And generally, if you have x cubed, it will be 3 times VP of X and so forth. And they're all different because this is strictly non-negative. So that's at least, this is really twice of that, and it's not the same. And so forth. And so you can actually, in retrospect, apply the strict triangle inequality, if you want, and you get that this is at least, and that's the smaller valuation. This is a bigger valuation. So you take the minimum, which is this. So that's why this is. So we can use it all the time from now. So this once more today. So that's why. But you can kind of understand, if you have a function, it has a 0, and you take a polynomial of that function, you compose the function, a polynomial over that function, and it doesn't have a constant term, then you can only increase the number of zeros. The factor will be exactly actually the smallest appearance of X. And you can see it from here. But anyhow, we know that. So this means, so I did it for every PNS, but in terms of truncated divisors, so what I'm saying is this thing. Right, so for every PNS, this is true. So just writing it like that, accumulating everyone, this is what you can write. Okay, and why am I writing it like that? Because I told you it's a mouthful lemma, but it's an important one, so it's worth doing it like properly. So now let's look at gx times y. Recall I want to prove that gx times y sits here, right, in L0s. So gx times y, well, y is in LAS, which I never used so far. So this is in gx LAS, just because y is in LAS. Or maybe I should, yeah, that's true. And then, do you remember if you have a linear, like you multiply a function by a Riemann-Roch space, it's really another Riemann-Roch space. It's this one, right? And do you agree that I can also put an S here? Because nothing changes. It's just easier to see what I want to write now. No, this one. This one. Because who cares what happens outside of S? Right. Good. And this, where is it? Yeah, this A. Just a short name for A for us before. So you see that restricted to S, this is larger or equal than A. So this means that this is non-negative. Right, restricted to S. Like, maybe I should say that or something. Restricted to S, this is non-negative because it appears here. Non-positive. Okay. So this means that this is inside L, technically 0S, but I don't care. It's the same L0S. Yeah, it's a bit. Good. So let me just state the corollary that we'll have. An easy corollary, I'll prove it after the break. So this lemma by itself, I don't know if it's so. No, it is, yeah. So I mean, okay. Right, that proves the thing, and then the corollary is obvious, so maybe I just write it and that's it. Corollary free in the notes. So for every non-zero function, everything is a divisor. The pole divisor, zero divisor, and therefore the principal divisors are all divisors, no more pseudo divisors. Right, because we did it for x0 or x infinity, I don't remember, but you can do it for the other one, and then that immediately implies that also x is a divisor, as the sum of divisors. Moreover, here it says for x in f and not in k. I think it's for every non-zero function, but I didn't want to. You can actually bound the degrees. So the number of zeros counted properly, like counting with the degrees of the divisors, which really says counted with multiplicity in a sense. No, it doesn't. The number is the multiplicity. Counted with respect to the field extensions. That's what it means. Anyhow, forget about that. That's at most this number. And that's actually equal to that number, but that comes later today. So that's what we just proved. And that's a good result. Okay, good. So after the break, we're going to prove essentially equality. We are not going to see Gopa codes today. Okay.